So we've looked at spontaneity, which is the overall idea. Does a reaction give off energy or absorb energy? And we realized that that's not entirely determined by enthalpy, delta H. So there's another piece to it that we need to consider, and we're going to define that right now, and it's called entropy. And entropy, which is defined by the letter capital S, is a measure of disorder. And so this can be looked at in terms of reactions or processes. Is the reaction becoming more disordered or less disordered? And that's something that we need to consider when we're looking at the overall energy loss of a given reaction or a process. So we're going to be talking about delta S, a change in entropy, the entropy final minus initial. And we're going to look at this in terms of processes and reactions. And S is a measure of disorder. So if delta S is positive, that means the reaction or the process is becoming more disordered. And we're going to find out here in a little bit that this is favored, that the universe and in general things tend to like being disordered, that it's very easy to make something disordered. Likewise, delta S, if it's negative, it means that the system we're looking at is becoming less disordered. Okay, which means more ordered. So I tend to talk about it in terms of delta S is a measure of disorder, delta S positive, things are becoming more disordered, delta S negative, the things are becoming less disordered. But this also means, it's becoming more ordered. And this is the idea that making things ordered actually takes energy, and that's something that we need to consider when we're looking at the overall energy gain or loss for a reaction. So a good idea of this is, to see entropy in play is looking at two gases mixing. And so this process has a delta H of 0. We don't need to put energy into it. But the idea is it still happens. It's a spontaneous process. So when you have two gases and we have them separated and remove the separation, the gases mix spontaneously, but there's no enthalpy involved. The delta H is 0. So there's another piece. So this reaction is spontaneous, so there's something else going on. And that's disorder. So we look at this. This is kind of the classic example. I have two gases, A and B. It's separated by a partition. If I remove this partition, spontaneously these two gases will mix. I don't need to do anything about it. That the gas A and gas B will intermix, and I don't need to put energy into this, but yet it still happens. So systems spontaneously tend to become more disordered. And now you can kind of see this, that disorder has to do with energy. If I wanted to go back to my original starting state, I'm going to have to apply energy into the system. I'm going to have to literally go in there and separate gas A and gas B, and that's going to take energy to do that. So here, two gases mixing, it's a spontaneous process, but the enthalpy is 0. I'm not putting heat into here, but yet it spontaneously happens. And so disorder is going to be part of our thermodynamics, and we're going to have to add that to enthalpy to get the overall thermodynamics for a process or a reaction. So some things that you can relate to in terms of a positive delta S. So some things that are becoming more disordered. And there is two different ways that we can look at disorder. We're going to find out there's ways of formally calculating a number, and then there's ways of kind of looking at it and deciding based off of our knowledge of disorder itself. So some things with a positive delta S, things that are becoming more disordered, is a solid turning into a liquid. So in solids, the atoms are linked together, they don't move, but in liquids, they're fluid. The atoms actually move around. So it makes sense that liquids are generally more disordered than solids. And likewise, turning a solid or a liquid into a gas, that is also a situation where we get a positive delta S. So if I have a solid, the atoms are actually locked together, and when I have a gas, the atoms aren't touching anymore. So it makes sense that the disorder is increasing, so delta S is positive. So looking at a reaction, we're going to find a couple of ways to actually do a formal calculation where we get a number out, but in terms of predicting for a reaction, it's a little difficult. But one way that we can look at it is if the number of moles of gas is increasing during a chemical reaction, the reaction tends to have a positive delta S. So this may not always be true, but it's a way that we can estimate that. So if I'm producing more gases during a reaction, it makes sense that the delta S for the reaction is going to be positive. So we look at delta in a gas. So if you remember, we talked about delta in a gas when we were transferring Kc to Kp. We had to look at delta in a gas. And delta in a gas is really just the number of moles of gaseous products minus the number of moles of gaseous reactants. And so we'll look at an example of this here in just a second. But we're talking about the stoichiometry. And so we're adding up the stoichiometric coefficients for gaseous products and subtracting the stoichiometric coefficients of gaseous reactants. So remember, we're looking for the subscript G. We don't look at subscript L and subscript S. We're just looking at gases. So another process that has a positive delta S is just in general increasing the temperature of whatever system that we have. So temperature is really this kinetic energy that's inside of the molecules. And so by increasing the temperature, we're increasing this movement inside of the atoms that is inside of our system. So in general, increasing the temperature of a system tends to increase the disorder. So delta S is positive. And likewise, if I take a solid and dissolve it in a liquid, so once again, a solid, the atoms are actually touching. Now when I put it into a liquid, the atoms break apart. So this tends to be a process with a positive delta S. So let's look more importantly at some situations here. And overall, we're just going to estimate whether the delta S is going to be positive or negative, the enthalpy of a given situation. So if I give you a reaction and I don't really give you anything else, it's best to look at the delta in a gas. And the delta in a gas will have a specific sign, positive or negative, and whatever the sign is on our delta in a gas, that's going to be the sign on our delta S. So here I want to look at the gaseous products minus my reactants. So my products are water and CO2, but water is a liquid, so I ignore that. CO2 is a gas. Remember, there's an implied 1 here, and that's my 1 here. So we'll only have one gaseous product, and then I subtract gaseous reactants. So both my methane and my oxygen are gases, so I consider them both. There's an implied 1 here. There's a stoichiometric 2 here. 2 plus 1 is 3. So my gaseous reactants are 3. So overall delta in a gas for this reaction is 1 minus 3 or minus 2. So we're reducing the number of moles of gaseous species inside of this reaction. We're becoming less disordered, so my delta S is negative. So this is a way that you can kind of estimate that. How negative, we don't know that. We'll look at some ways of doing this reaction. So here's another example. I take ammonium nitrate and I dissolve it in water. So I'm taking solid ammonium nitrate, turning it into aqueous. We've learned that up here, and we can kind of envision this. I take a solid and I dissolve it in a liquid. The solid breaks apart. The ammonium and the nitrate separate. We're becoming more disordered, so delta H is positive. So as we become more disordered, delta H is positive. So another one here, let's look at this. We take gaseous water and turn it into liquid water. So we're taking a vapor and we're turning it into a liquid. So this is a condensation, and we're going to look at these phase changes here a little bit more. But the idea is I'm taking a gas where the atoms are not touching each other, and I'm turning it into a liquid where the atoms are touching each other. So we're becoming less disordered. So delta S is negative. So here we're going to start applying delta S along with delta H to get a new kind of overall number called delta G, or Gibbs free energy. But for right now, the units on our delta S involve a unit of energy. It's kilojoules per mole, but we also need to have the temperature. So temperature affects disorder. So it's kilojoules or joules per mole Kelvin. So because these numbers are kind of small, a lot of the times they will try to slip in a joules per mole Kelvin. And so that's going to be one of the main problems, is that delta H's tend to be in kilojoules per mole. Delta S's a lot of times are joules per mole Kelvin, and we got to make sure to convert them to kilojoules per mole Kelvin if they are given like that.